As I didn't. You're sure you didn't have a second file because it will be really bad.
Okay. Yeah, you're on. Hello. Good afternoon. Hello. Good afternoon. Welcome to this afternoon's session of the live oral presentations for T3.1. The session today will be on the design of sensor systems, advanced sensor technologies, and this is an oral session. So first of all, let me welcome the speakers today. There are 6 presentations, and I will just quickly go over the names of each of the presenters. The first one will be Gabriel Cochot. The second one will be Monica Risa. The third will be Shaji Matthew and a bunch of other collaborators. The third will be Jeffrey Cram and a bunch of collaborators. And the, sorry, that was the fourth. The fifth will be Carrick Talmadge. And the sixth and final one will be Paul Vincent and his collaborators. So without much ado, I think based on the schedule you all got before, you know your turn. And just a few basic rules. I think everybody knows you have about 15 minutes for your presentation. If you have already and wish to have your presentation pre-recorded, then we will make sure that the presentation is started and played. And then as it ends, there'll be time for 3 minutes of question and answers. If you wish and would like your presentation to be manually done live, then feel free to do so. But we would strongly suggest, unless you're unable to drive the presentation from your end, if you would like, communicate that to us, and then we will, but you need to tell us to step to the next one. So without much ado, I think in the interest of everybody, to give everyone time, I'll begin with our first speaker. So I'd like to have Gabriel Cochot begin, please. And his presentation will be update on xenon adsorbent development at CEA. So go ahead, Gabriel. Could you please start speaking, and then we'll step through the next one you need to tell us to step through.
Yeah, but actually, as I say, I would prefer to use the pre-recorded one if possible.
Okay, so just a second, and we will ask our team to start his pre-recorded presentation. Could you please start his pre-recorded presentation? That's what he prefers. Carlos, pre-recorded. Not possible? Okay, it's not yet up here, Gabriel, so can you please orally do it right now? Thank you.
Okay, I will try, but I have to say that I'm not really prepared for this way. So okay, I will try. Okay. So my name is Gabriel Cochot. I'm working at CE Adam as a engineer research in physical chemistry, and I would like to present to you some aspect of material development in our laboratory. Actually, I have not the visual of my presentation appearing on my screen. Can you help me with that?
Second, the people are working on that. Yeah. Okay, it should be. Go ahead. Yes, Gabriel, go ahead. It's all, we can see it here.
Okay, but it still not appear on my screen, so I'll try to make
we
a
can see
PO.
it here, so it's being broadcast.
Just some second, please. I'm trying to make a presentation up here on my computer, so I can make the audio on at the same time. Just some second, please. Okay.
You want to share?
Yeah.
Stop sharing on the site that he shared.
So I have a version, but it's not exactly the same. So in slide 2, as you can see, we are working on a Spalax NG process. All you have to know about this process is adsorption is a very important thing, as long as adsorption is used in order to concentrate xenon present in the air. So in Spalax NG, which is manufacturing by Sigilec Defense, there's 2 parts which are using adsorbent. First part is purification step, which is using thermal swing adsorption and activated charcoal in the column of around 150 grams. And in the concentration step, which are using zeolite, ZSM5 zeolite in a column of around 3 grams. So conclusion of this part is adsorption is very important in this kind of process. So can switch to next slide. It should appear a timeline where we are planning to make a screening. Normally, in the next slide, it should be up here some isotherm, right? You hear me?
Yeah.
Normally, you should have 4 isotherm on your slide, right?
Yes.
Okay. So on this slide, I would like to show the 2 important things. You can click to make up your first animation. First thing is in the development of the light, we find that the use of silver improve xenon adsorption performance, especially in low partial pressure. And the second thing is, among all the zeolite tested in our laboratory, AGZSM5 is the one which shows the best performance concerning pure xenon adsorption. So after that, we have performed other kind of studies. So normally, if you click, it should appear the AGZSM5 study, a specific study concerning AGZSM5, right? So in your, it should appear 2 graphs and a table on the right. Is that okay for you?
Yeah.
Okay. So here I would like to present to you a specific thing. When you have some interest in the HZSM5 zeolite, there are 2. We can see 2 kind of sites, site 1 and site 2, which are specific of a double long isotherm. So we perform Monte Carlo simulation. So I think you have to click in order to make the animation. And thanks to this simulation, we obtained 2 things. We identify that Sit1 is due to zeolite structure, and Site 2 is due to silver nanoparticle interaction with xenon. And if you click, normally you can see the table up here and see that the parameters used in the Monte Carlo simulation are quite in agreement with the experimental observation in terms of average silver nanoparticle size and in terms of weight ratio of silver. So in such a way that we can use this model as a predictive model for other noble gas. Then we study other things. So if you click, you can see we also work on structure property relationship. It should appear just a graph on the left, which represents isotherm with several kind of AGZSM5. So this isotope represent. I would like to show that depending on the structure of Agility-Sensing, even if the material have the same characteristics, you can click and it shows that there are very different properties. So if you click, we can see other analyze like aluminum and NMR or microscopy pictures. And with this complementary analysis, we can see that depending on the structure of the zeolite, it leads to different properties. So that's why the relation between the zeolite structure and material property is very important. And it's very important to master the structure of the zeolite in order to determine, to determine property tolerance. So that's it for this slide. Now you can move to the next slide, which should be related to ab initio study. We perform ab initio study using a DFT calculation using ab init code. We perform for the moment the simulation using 13 atoms particle. The first aim of this simulation is to relax the nano silver particle, and then we determine the energy between the silver nanoparticle and a xenon atom, and find out that the minimal energy was found for a binding energy of -21 kilojoule per mole and a length of 3.2 angstrom. So this study shows that the status of the bond seems to be a more covalent bond with some van der Waals effect, which is not very intuitive for chemistry for gas demand. So we can move to the next one. So we choose to develop the study for in upscaling. Then we use this kind of pilot in order to make the scale. So it's a research pilot where we can use more extensively Agility-Sensing. With this pilot, we study a lot of parameters which are listed here. The role of this pilot is, for example, to determine the parameters of asymmetric function depending on flow rate and temperature, and then try to link this parameter depending on the studied parameters. The final role is to be able to determine and to predict the elation curves depending on the condition. Then we study the deactivation. When we put Agility-Sensing in a process, as you can see, we identify in the head of a column a phase of silver chloride, and then we can see that there are larger nanoparticles in the process. So we find out that if the adsorption phase silver reacts with some chloride compounds in order to form silver chloride, and in the desorption phase we partially regenerate silver. We have some sintering and a progressive decrease of the performance as shown in the left figure. So this leads to the perspective. Is that right for you? Is it the same?
Yes.
Okay. So thanks to all of those tools, we are able to we'll try in the future to identify some other efficient adsorbent using screening of xenon with other metal using ab initio study. We'll try to make a synthesis with this new identified metal on zeolite structure. Then we'll try to improve the performance of Agility-Sensing using a large variety of Agility-Sensing structure, and try to find out which is the best structure which lead to the best properties, and finally try to upscale the best submaterial we finally find out. So sorry for the presentation. It was a bit hard for me to perform in this condition, but I hope to enjoy the presentation. And I will be glad to ask your answer your question if you have some.
Okay, thank you, Gabriel. We heard your presentation and we saw the slides. And at this time, we have plenty of time for questions. So I suggest the participants and audience to kindly submit your questions, please. And then we will provide them to Gabriel so that he can answer. Is there somewhere we can see the Q&A screen? Because we can see nothing. So please hold with us, and I strongly suggest the participants and people who are listening in who have questions about Gabriel's presentation on the SEA development of xenon absorption technology to please submit questions, and then we will provide them to Gabriel so that he can field the answers. So
How many questions so far? This from a different session.
okay, so far we haven't received any questions, so maybe we'll go back to Gabriel, and if Gabriel has anything important he'd like to pass on in terms of the significant achievements in his development that he'd like to pass on, what were the biggest steps that made the breakthrough that he achieved? Was it in finding the right material? Was it in performing the studies which helped him guide to select the best material to be used? Or, was it the actual performance of the material that was used? So, Gabriel, you have a few minutes. If you'd like to, you can take over and speak. Go ahead, Gabriel.
Yeah, actually, not a lot to say about it.
Okay. But in terms of, I have one question, just very broadly, in terms of absorption, how many percent, were you better than what was used before? Very loosely. Was it 50% improvement, 100% improvement, 200% improvement? Gabriel, are you allowed to say?
Yeah. I mean, it depends. It really depends on comparison. For example, when you use silver zeolite, sorry, in general, when you, for example, charcoal.
Yes.
In comparison, whatever the zeolite is, are really better in terms of adsorption. But here I made a focus about adsorption in terms of thermodynamics, but you also have to consider how to say diffusion. For example, you can have a really performant material in terms of absorption capacity, but you also have to look at the diffusion of the material. If you are a very efficient material in terms of adsorption, but very poor properties in terms of diffusion, that makes the development material very difficult.
Okay, Gabriel, I have a real question from the audience. We have someone who says it was very great work and thanks you for the great work. But for the future, he says, with the ab initio study, have you some ideas on potential metals of interest? Do you have any? Yeah.
For the moment, we identify some interesting metals. So in the past, we found out that what we call polarizability of the metal can have some effects with xenon adsorption. So we identify some metal we have various polarizability in order to check if this parameter specifically can play a key role in xenon adsorption. And concerning your later question, I would like to point out the fact that relation between structure and property is really something. I mean, for the same material, exactly on the paper, you can have some significant difference in terms of properties. So even if you find a really good material in terms of adsorption capacity, in terms of diffusion, you have to check out that your material will work whatever the batch is, whatever the supplier is, and that's really an issue.
Okay, and the other question, there's another question. They want to know how long this work, what is the duration of this work, you know? How long is work going on for, or process being developed? What's the time scale?
Concerning ab initio study or concerning the
in general?
In general. Yeah, it's quite a long time because you have to check several parameters. So I think starting from the start to the development of new identified material, I think it's something like 5 years, maybe 10 years. But finally, you can something interesting because, for example, in the case of ZSM5 in comparison with activated charcoal, we have a significant gain, which is something like 10 in terms of xenon capacity. So which means we can decrease the quantity or the mass of adsorbent by a factor 10, which is really significant. It changes everything on the process.
Okay, I think it's very interesting talk, and there are lots of follow-ups, but we're out of time. So thank you very much for your presentation, and we need to now move on, Gabriel, to the next one. So if there's plenty of time all through this, just to remind people, if there are follow-on questions, this is an online conference, you can still submit questions, and we will provide them as to the participant to respond to you directly, but not in this live forum. So thank you very much, Gabriel, and we move to our next speaker, please. The next speaker is Monica Risa, and she's going to talk about radiation detection for OSI, influence of firmware on detector performance. Go ahead. I think she'd like a pre-recorded presentation.
Monica Risse, and I'm part of the business unit Nuclear Security Policy and Detection Techniques of the Fraunhofer INT in Germany. Well, I'm glad to have the opportunity to talk to you about results we have obtained during qualification tests of radiation detection devices. In there, we could observe the influence of different soft and firmwares. For on-site inspection, it is very useful to have small devices, which are easier to handle than larger equipment. The miniaturization was very successful over the last years, and one step was to substitute the NIM hardware by high-performance digital hardware and to implement digital data evaluation methods. But also the use of novel detection materials is a part of this. Well, the radiation detection devices consists of a detection unit and the signal evaluation unit. The detection unit can be subdivided in the detector material itself, the pulse processing unit, here I would for example include photomultiplier and amplifier and something like that, and something like a counter, for example a multi-channel analyzer. Well, the firm and software releases are relevant for the performance of the components, the signal components, and of course for the whole detection results. And they are much more important in this digitized version than in the conventional systems where the hardware is much more important. Now I will show you the device we used for exemplarily study the effects of these. It is the D3S from Chromic. It is one system which consists of two parts: the detection unit, which can be worn on a belt, and the smartphone for data collection and display. Both are connected via Bluetooth. The detection unit has a cesium iodine crystal for gamma detection and a lithium-based one for neutron detection. As it is rather small, it uses a CPAM. The D3S can either function as PID device or as RIT. We do have two devices, an older one with hardware from 2016 and a newer one from 2019. The older one had originally this firm and software, and I indicated this by adding a V1 to the old.
It stopped, but please hold and then we'll get it continuing.
As well of the firm and the software. Which tests can be used to investigate the influence? There are 9 software releases between the two versions. I have listed some of them here. So you see that there are several dealing with dose calculation. Therefore, it seems reasonable to check the results from the accuracy tests for dose rate measurements. Well, here you see the D3S tested with our qualification test system for radiation detection devices, Q-test. In the back you see the source. There are several specifications and common standards like ANSI, IEC, and IEEE plus 10 for the different device classes. I have listed them here. Given are the allowed percentage deviation and the foreseen dose rate values. In our case, the maximum dose rate given by the manufacturer is 15 microsievert per hour for the older D3S and 20 microsievert per hour for the newer one. For the tests indicated with the orange background, only cesium-137 is used. In all other cases, to cover the whole energy region, also tests with americium-241 and cobalt-60 have to be done. You see, prior to the testing, you have to know in accordance to which standard you want to do the tests. Well, we started our Q-test within the IEEE plus 10 program. This is why we have done tests in accordance to that specifications and for the dose rates given here and with all the 3 nuclides. Here you can see the results first obtained with the cesium-137. So if you plot the dose rate obtained by the D3S against the dose rate measured by reference device, you should have some points on this red line. Well, here you see the results we gained with the old system. Well, the D3S values do not match, but what is the percentage deviation? So therefore, I will plot the percentage dose rate deviation against the dose rate of the reference device. These are the same data as you saw before, and you can see the large deviation. Next are the values obtained for the new V2. The values match better at lower dose rates, but they don't match well at higher dose rates. It is an impact of an hardware or the firmware software. Let's see the old V2 results. They are nearly the same as the results for the new V2. Therefore, we can say that in this case, the change of the hardware has nearly no impact, and the change in the firmware software has a big impact. What does it mean for accuracy tests results against the standards? The deviation of these two values is much too high for all standards, and the V1 device would fail all tests. The specifications for the RIT and PID devices for ANSI standards only foresee a cesium-137 testing, and the dose rate accuracy is only tested in this region, and the load deviation is plus minus 10%. So the D3S will pass the accuracy testing according to the ANSI, RIT and PID standard. For SPID, higher dose rate values are started, 70 microsievert per hour, and the device would fail that test. I don't want to go through all in detail, but I can tell you that the D3S V2 passed the cesium-137 part of all IEC tests, but failed the ones for the ITRA plus 10. So look at the cobalt results. You see here the results gained with the old V1. They seem a bit better than the ones obtained with the cesium. And the new V2 results you can see here. So you see that there is an impact in the low dose region. Well, I cannot exactly say whether it is from the hardware or from the soft and firmware, as we have not done the measurements with the old V2 combination. But as last nuclide, I show you the results obtained with the americium-241. Please have a look on the scale. The deviation is going up to 2000%, where it should be 0. So you see the old V1 results with the deviations above 1000%. We want to check whether it is an artifact or not, although the data are mean values of 30 single measurements. So we did some more measurements, and you see that they show the same effect. How is the effect with a different firmware software? You see here the blue stars. The values are much lower. So the firmware software has a very large impact. How about the change in the hardware? In this case, again, it is nearly no impact. But let's have a closer look on the V2 values to evaluate the accuracy test. You see that the deviation is mainly above 50%. The D3S would fail all accuracy tests with americium-241. This shows the dependence of the accuracy results on the radiation energy. And by this, I'm nearly at the end of my talk and come to my summary. A measuring device must be assessed as a whole system and not just the individual components. The change of firmware software has a very big impact. I could show you this on the example of accuracy measurements on the D3S. But please keep in mind that PIDs, SPIDs, RITs are not intended to be used for radiation protection purposes. My advice is, be aware of which firmware software you use, especially if you have several devices, and take the advantage of available updates. Also, the performance of the measurement devices may generally vary with the dose rate, as well as the energy radiation is relevant for the result. Therefore, extensive testing of the devices is necessary with not only one nuclide. By that, I thank you for your attention and would be glad to answer your questions.
Thank you very much. That was a very interesting presentation. We have a few minutes for the audience to send their questions using the Q&A screen online, and then we will give Monica some time to present this. So, Monica, one of the questions that has come is, thanks for the very interesting result. And what they are interested is they would have liked to see the results plotted as a function of isotopic energy. It seems that the devices may be intended for intermediate range cesium to cobalt, cesium-137 to cobalt. Cesium is 662 keV, cobalt is 1.37 MeV, 1,300 keV. So do you have an answer, a good answer for this person, please? Thank you.
Sorry, forgot to unmute. Yeah, that's what we observed, that there is a big dependence on the energy, and yeah, sometimes they have problems with lower energy, sometimes with higher energy. It's really depending on what system you're using. So this was just exemplarily our study that to show that there is really a dependence and that you have to keep this in mind when using such devices. In this year, there was clearly a problem with a low dose, with a lower energy. But as you saw, during when they changed the soft and firmware, and prior to that, they really overestimated the dose rates, and afterwards they underestimated. So you really have to be careful about this.
Thanks. Thank you, Monica. Interesting question. I have a question for you. You know, your calibration measurements in your Q test basically gave you some results where you see a very repeatable, you repeated it many times, curve which shows you the dose rate as a function of energy for a particular type of measurement. My question to you is, could you not then use that as a calibration curve within the firmware to then give the right result? Because you already know that your deviation is a specific one. And then in the end, with the correction, you'd get, you know, a more correct answer after the correction's been applied. You see what I'm getting at?
Yeah, that sounds good, but you know that the device is not. We just bought this device, so it's we are not doing this. So you have to talk to Comic that they shall implement this maybe.
Okay, but as a suggestion, I think a closer collaboration between a group like your group, you know, a reputable institute like Fraunhofer and the vendor would make a much better device for the users, because it's not so good if Chromac has something that's imperfect, and it's not so good if you know what the imperfection is, but it's just a scientific paper. Yeah, it would be good for the community that it kind of merges. So strongly urge that, you know, you'll get, especially for OSI, that this is all merged together, and then either the device that comes to OSI use has the right corrections, or Chromac provides it at the beginning. Thanks very much for your time. We're out of time now. We'd like to thank you for your time. And with this, we move to the next speaker, which is Shaji. He'll be talking, Matthew, he'll be talking about detecting underground nuclear explosions, related dynamic phenomena using time-lapse seismic surveying. So just one of the things, Shaji, I'd like to point out, if you are choosing to have the video played, then you shouldn't do it from your end. It'll be done from here. If you are showing the slides live, then go ahead and show the live slides and speak. So with that, you can start.
Okay. Can you hear me well?
Yes.
All right, okay, I'll try to share my slides and see how it goes. If it is not working well, maybe. So what, can you see my slides? Is it,
Yes, I can see. Yes.
Is it the right one or with the notes?
Well, it's just a slide. I don't see any notes.
Fantastic, right.
Yeah.
All right, okay, so hello everyone. So today I will be talking about the application of time-lapse seismic surveying for detecting explosion-induced dynamic phenomena. So in this presentation, I will discuss the potential of this method, the challenges, and how machine learning can be employed to overcome these challenges. So this is the outline of my presentation. First, I will give an introduction to dynamic phenomena and its timescale associated with underground nuclear explosion. I will look at the impact of seismic property variation associated with these temporal phenomena. Then we will look into the potential of time-lapse seismic for the detection of 4D signature caused by these phenomena. We will also discuss the potential challenges for the detection. I will then show how machine learning can be employed to overcome the main challenges during OSI. Then in conclusion, I will discuss the limitations and give some comments. So the dynamics of energy distribution and the time scale of observed phenomena following an underground nuclear explosion is shown in this curve. During the very initial moments following the explosion, huge amount of energy is released in the form of heat and shock wave. This causes permanent rock deformation such as cavity formation, rock fracturing, and groundwater mounding as a result of increase in pore pressure and rock compaction. Later on, when the pressure diffuses, the cavity wall collapses and groundwater infills the cavity. Then after a few hours, we start to observe the dynamic phenomena due to residual thermal energy redistribution, residual pressure, and groundwater mound dissipation. So the objective of this project is to study the feasibility to detect 4D signature associated with these dynamic phenomena using time-lapse seismic. So amongst these phenomena, the groundwater mound dissipation, which is a function of residual thermal energy, residual pressure, saturation, porosity, and permeability, has the most significant gradient of dissipation during the initial 100 days following the test. The magnitude of these post-explosion residual energy is maximum near the explosion center, and these transient phenomena will cause variations in rock properties. The animation shown here shows the character of groundwater mound dissipation as published by Knox et al. And the image to the right shows the schematic representation of the groundwater level differences following detonation as published by Lasnek. So we carried out a numerical modeling study using Gassman equation and to understand the change in velocity variation due to this groundwater mound difference. The figure on the left shows the velocity at the base case condition where the groundwater mound is at the highest level. And the second figure on the right is the velocity of the monitor observation or the second observation after the groundwater mound has been dissipated. So the plot here shows that delta V by V shows that around 30 to 40% decrease in velocity due to the groundwater mound change. So this modeling study represented here does not consider any mechanical heterogeneities. However, publication by Bonal et al. Showed that in 2015, she showed that the effect of halo or heterogeneity on seismic velocity is very minimal. So again, Knox published that the rate of groundwater depletion is about 50 centimeter per day in the first 150 days after explosion. Though the gradient will vary for different geological scenario, however, observations at different test sites show that gradient is significantly higher during the initial 150 days time period. So after this period, the gradient is very small to be detected, and the seismic during the detected by the seismic during the OSI period. Therefore, the most likely period for detection during OSI would be if the inspection is carried out during the very early days of the test. So the change in seismic property due to groundwater mount can be observed using time-lapse seismic monitoring. So time-lapse seismic or 4D seismic is an oil and gas industry trusted technology used to monitor production changes at reservoir level. In 4D seismic, base and monitor surveys are acquired using same survey parameter, and the differences of these two surveys are after careful processing will highlight the changes at the target level. For OSI, we propose to use a similar technology by carrying out frequent seismic observation during this inspection period. So has this technology been used before? Yes. Similar frequent seismic observation has been previously tested in Canada Peace River field, and it is well known as Seismovie technology. For Seismovie, source and receivers are buried, and so produces very good repeatability. And it is very sensitive and detects time shifts as low as 0.05 millisecond, which is very, very much appreciable. Now, the image on the right is an example published by Schwartz et al., which shows the 4D difference without any 4D matching. It's a straight difference, and it still highlights the change in the reservoir level. So, but when it comes to implementing this technology for ISI, there are several significant challenges. One is the repeatability. For 4D seismic, it is essential to have a very good repeatability. Near surface has significant impact on the seismic repeatability. So Backlin et al. Show that we can achieve very good repeatability if the source and receivers are buried. Comparison in this seismic section, published by Backlin, shows that when the geophones are surface laid, the events or the reflectivity or the continuity of the reflection, events are very poor. Whilst when the geophone is buried, the image is significantly improved and the continuity improves significantly. However, for OSI, we are restricted to the surface laid source and receiver option, which provides very poor repeatability. The second challenge is the time constraint due to the treaty. In 4D processing, base and monitor surveys are carefully processed and cross-equalized or masked to highlight the 4D difference at the target. Often these workflows are quite time consuming, and therefore a workflow using machine learning is essential for 4D detection, which can be easily implemented in the field. So a workflow using self-organizing map, which is an unsupervised machine learning, is proposed, which would help to detect obscure time-lapse signature. Self-organizing map is a type of neural network that is trained using unsupervised learning to produce low-dimension discretized representation of the input space of a training sample called a map. Self-organizing maps are well suited for multi-dimensional data analysis and anomaly detection. And in this instance, it will be a 4D signature. So in this workflow, we first generate instantaneous attributes such as quadrature amplitude, envelope, instantaneous phase, instantaneous frequency, sweetness, etc. from all the seismic monitors that we observe. Then we generate 4D attributes, which is the attribute versus time for all the attributes. This helps to detect dynamic variation of instantaneous attributes. So AVT attributes such as intercept and gradient, a product of intercept and gradient, are given as an input to the self-organizing map. So following the SOM training, we compute the quantization error, which is the distance of sample from the best matching unit. The anomaly or the outlier cluster will have a high quantization error value, and which is what is shown here. The benefit of this workflow is this: we can do progressive SOM analysis by introducing new data points or new monitors and build confidence.
You have a couple of minutes left.
Yeah,
thank you
for the edition. Yeah, thank you. So workflow is tested using the synthetic study, and the velocity model of base scenario is shown where the initial groundwater mount is shown here. And we then generated 10 monitors introducing time-lapse changes, and the random noise was added into the near surface to mimic the realistic changes. And 121 shots were recorded, and we generated RTM stacks. So let's look at the results. These are the 4 monitors that we introduced. And then these are the 4D difference. So without a careful processing, we won't be able to you isolate where the 4D change is happening. So with the machine learning, we can actually see it highlights the region where the 4D change or the time-lapse change is happening, which is a zone of our interest. Now, we haven't considered the heterogeneity. Now, when we introduce the heterogeneity, we can see that the 4D signature is behaving very different to what the normal behavior is. So without the help of the machine learning, we won't be able to identify where the 4D changes. So here's the comparison between no heterogeneity with the heterogeneity. And when the 4D, when applying after the machine learning, you can see that the zone of the 4D change is clearly highlighted by the machine learning workflow. In conclusion, the groundwater amount dissipation, which is a function of saturation, pressure, temperature, permeability, is a significant dynamic phenomena observed during following an underground nuclear explosion. This phenomena is generally observed if the explosion is carried out in a saturation zone, which is within 80 to 100 meters of water table, which is one of the limitations. And the gradient of groundwater mound is very prominent during the 150 days following the OS, and therefore having an OSI inspection during that period would provide the best detection window. And machine learning workflow presented here would help to implement this technology in the field for OSI. I want to acknowledge EPSRC and AWE for funding this project and the Hydroacoustic University for helping me to carry out this project. And these are some of the references, and thank you for listening, and I'll be happy to answer your questions or receive comments. Thank you.
Thank you very much. We don't have too much time for questions because we are over time, but maybe one question. Yeah, so we'll have a question from Joseph. Go ahead, please.
So I'm wondering about the time frame that it takes in order to train your machine learning model. So if you're going to a different deployment location and you have different parameters of the subsurface, what kind of time do you need in order to train the machine learning model and then run it?
It will not, because this is based on the self-organizing map, and we will generate the attributes very quickly, and that is the best thing about the self-organizing map. It doesn't require much of a training. It is not like any other neural network or the machine learning workflows such as CNN or a deep neural network. It doesn't require that much of a training with the data set. What it requires is an attributes, carefully selected attributes, and we feed into the self-organizing map neurons, and that will essentially generate the attributes. So it is a very quick process that is very efficient to detect. That is why this technology is very good to implement anywhere. That's what I thought.
Okay, so we have another question. Can you very briefly, this is the last question, explain the impact of cavity size and depth in these cases?
So for this analysis, we have used the depth of about 500 to 600 meter is the depth that we have considered for this analysis. And the cavity size, I think I've taken like 10 meter or 5 to 10 meter. That was the cavity size that has been considered for this scenario. So that is the radius, 5 to 10 meter radius. Yeah. But the main point is it detects, it is not based on the cavity size, it detects the dynamic changes, which is the groundwater change. That is what is triggering it. So when it comes to OSI, we'll be looking into geological deformation, which has got this time-lapse change. That will be an indicator where the ground zero is.
Okay, thanks. With that, I think we've wrapped up our time and gone over. Thank you very much, Shaji. We move on to our next speaker. Again, you have 15 minutes. Please keep your time. I think try to end around 12 minutes, because then 3 minutes for questions. If you don't, then we have only time for one. So the next speaker is distributed optical fiber sensing and potential applications for IMS hydro stations. And the speaker will be, please, the speaker, can you identify yourself, because it's a bunch of guys.
It's Jeffrey Cram, first name on the list.
Okay, go ahead, Jeffrey. You're live.
Well, it's pre-recorded, so I can invite you to go ahead.
Yeah, thank you, Jeffrey. Be ready, and we'll start. Thank you.
I'm an engineer at the Applied Physics Lab at the University of Washington. and I'm presenting on behalf of my colleagues Dale Weinbrenner and Kevin Williams of the Applied Physics Lab, and William Wilcock of the School of Oceanography at the University of Washington. I'll be discussing distributed optical fiber sensing and how it might be applied to the IMS hydroacoustic system. At the highest level, a distributed optical fiber sensing system is made up of two elements: an interrogator connected to a sensing fiber embedded in the system of interest. Inside the interrogator is a laser that sends light pulses into the fiber. Those pulses are scattered by features within the fiber. The majority of the scattered light is lost to the fiber cladding, but a small percentage is returned to a photodetector in the interrogator. It turns out that these features in the fiber are sensitive to environmental factors, such as temperature and vibration, which causes them to modulate the amplitude, phase, and/or polarization of the scattered light relative to the injected pulse. The interrogator compares injected to scattered light in order to measure those environmental parameters and ties those measurements to specific locations along the fiber based on time of flight. The parents of this technology are optical time domain reflectometry and the 1970s development of discrete optical fiber hydrophones. OTDR was originally developed to locate fiber splices, damage, and breaks, but was found to be somewhat sensitive to environmental conditions as well. In 1980, A.J. Rogers proposed a technique of polarization OTDR, which was subsequently demonstrated by Arthur Hartog in a single-mode optical fiber. A definite innovation, but sensitive to a number of parameters at the same time, so it had limited practical use. In 1983, Hartog reported on a short, liquid core fiber distributed temperature sensor that relied on Rayleigh scattering detected with an OTDR. The usable range was 5 to 110 degrees Celsius. In 85, John Dakin demonstrated Raman scattering temperature sensing in an optical fiber. And in 92, Euskaitis demonstrated vibration sensing using coherent Rayleigh backscatter in a 28-meter long fiber. This was extended to temperature sensing by Rathod in 1994. In 93, Shimizu and colleagues at NTT Labs demonstrated Brillouin scattering in a 10-kilometer fiber and proposed using it for temperature and strain measurement. Now let's take a closer look at the first of the three main technologies used in distributed optical fiber sensing, which is Raman scattering. This is based on interactions of photons and very small-scale molecular vibrations in the glass. Raman scattering is inelastic, meaning that the energy of the incoming photons is not conserved. Most of the returned photons have lost energy in the process and are thus lower in frequency. This is called Stokes-Raman scattering. A smaller fraction of them experiences the opposite effect, ending up having higher frequencies. That is called anti-Stokes-Raman scattering. It happens that local temperature along the fiber is a function of the ratio of the Stokes to anti-Stokes scattering intensities. Performance has been reported of temperature resolution as high as 50 microcelsius, spatial resolution ranging from 1 to 17 meters, update rates of 10 seconds to 10 minutes, and a maximum range of about 30 kilometers. Commercialization has been driven by oil and gas, but other industries have implemented it as well. The best thing about Raman scattering is that it's the most established of the three methods, so it's a very mature technology. The main limitation is the very slow update rate, driven by the weak backscatter signal. It has another potential drawback, depending on circumstances, which is that elevated temperatures and hydrogen absorption degrade the fiber, leading to increased differential loss, particularly of the anti-Stokes signal, and a consequent loss of calibration. Brillouin scattering is similar to Raman in that it's inelastic. In this case, scattering is from the interaction with acoustic phonons, which are lattice vibrations that cause changes in local refractive index driven by temperature. Both temperature and strain can be measured with this method, with temperature resolution reported to be about 10 times better than for Raman, similar spatial and temporal resolutions, and a maximum fiber length of 150 kilometers. Commercial use seems to be for a more diverse range of industries, mostly interested in strain measurement. The strong suits of Brillouin scattering are its extended range and the ability, in one incarnation, of millimeter-level range resolution. Like Raman, it has a very slow update rate. Rayleigh backscatter is a different kettle of fish being the result of elastic collisions between incident photons and refractive index variations that are frozen into the fiber during the manufacturing process. In this case, both frequency and polarization are conserved. Temperature and dynamic strain can be measured this way, with the principal performance difference being that this is a dynamic scheme, allowing vibration measurements down to microhertz and sampling rates of hundreds to thousands of hertz. The maximum range is currently 100 kilometers. The higher update rate lends itself to acoustic and seismic measurements, as well as other strain and temperature applications. Now that we've reviewed the fundamentals, let's look at some subsea applications. Recognizing the many offshore oil and gas systems that have been installed, here are three
10
scientific
minutes are over.
installations that I find particularly interesting. The first has been reported by Hartog, although to date I haven't been able to find any details beyond the bare fact that the Geologic Survey of Japan built a fiber-based distributed temperature sensing system for offshore hydrothermal vent exploration using battery-powered interrogators in marinized housings. In 2018, Nate Lindsay used Rayleigh sensing on the first 20 kilometers of the Mars cable at Mbari for a 4-day test, during which he picked up an impressive amount of information on multiple submarine fault zones, shoaling ocean surface waves, microseismic generation, tidal bores, sediment transport, infragravity waves, and breaking internal waves. In 2020, Matsumoto and colleagues with Jamstec connected OptoSense DVS equipment to the first 50 kilometers of a disused cable off Shikoku Island, operating at the same time as a nearby ship-based seismic survey. This happened near the DUNET earthquake and tsunami detection network, so the DVS response to airgun shots was compared to DUNET hydrophone data and found to have similar frequency response, although higher self-noise above 5 Hz than the hydrophones. I'd like to note that Matsumoto will have an e-poster on this experiment at this conference. This is a map of the CTBTO's IMS hydroacoustic network, showing the 6 hydroacoustic stations circled in red, along with the T-phase seismometer locations. The 5 island-based hydroacoustic systems each have 2 hydrophone mooring triplets with the hydrophones in the sound channel, and the system at Cape Leeuwin, Australia, has a single triplet. Taking a look at a typical IMS triplet, we have a seafloor trunk cable running from a shore facility to the first node. That cable, which varies between 21 kilometers and 10 times that length, depending on site, sends power to the nodes and carries the digitized hydroacoustic signals back to shore via an optical fiber for processing and transmittal to Vienna. All riser and internode cables carry the hydrophone signals in analog form via copper conductors back to the digitizer at the first node. The hydrophones are in the sound channel between 550 and 1350 meters above the seafloor. All this leads to some interesting thoughts about how one might consider augmenting an IMS hydroacoustic station with distributed optical fiber sensing. The simplest and least invasive approach would be to install a conventional DVS interrogator at the shore facility of an existing system, connected to one of the unused fibers in the trunk cable. This would allow immediate measurement of temperature, strain, and seismic data with minimal impact on the system as a whole. Alternatively, if and when a triplet were to be replaced, it would be relatively straightforward to incorporate a marinized interrogator into the base of node 1 of the new triplet, and to incorporate a continuous optical fiber run leading from the interrogator up and down the first 2 riser cables and ending at the hydrophone of the third. This would provide temperature, strain, and acoustic measurements along all 3 riser cables, and strain, temperature, and seismic data from the internode cables. Data acquired in this way would be very helpful to the scientific community, allowing long-term monitoring of key climate change, geological, and biological data from remote locations. And that's all I have for today.
Thank you. The presentation's over, and we have time now for a couple of questions from the audience. So, Jeffrey, the first question for you is, where is the sensor system placed? At the bottom of the water, or is it floating in the water? And how much sound pressure can be detected?
Well, the first question is easier to answer than the second one, for me at least. The sensor system is really, as noted, made up of two elements. The interrogator, which these days is produced by a number of manufacturers in the form of rack mount equipment. So that would be on land or above water typically. I refer to marinizing it, which would mean disassembling that equipment and putting it inside a 1 atmosphere pressure housing so it could be put underwater safely. The second element is the optical fiber, and the optical fiber can be in any form at all. It turns out that it's quite sensitive, even if it's buried inside an existing telecom cable with all the steel and polymer around it. But in terms of actual sensitivity, it very much depends on the circumstances and the nature of the cable itself around it. So I can't answer that question directly.
Okay, but I think your answer to the second part of the question was a little muddled. Is it floating or is it on the floor?
Oh, that's true. I didn't address that at all. The cable can be, I imagine the cable can be floating. Every implementation I've seen of this, the cable is typically in contact with the ground. The innovation that I'm talking about here is potentially putting it in the riser cable. So the cable itself is suspended by a float. So I suppose you could say the cable is floating. It doesn't really matter to the cable what its orientation is. What that dictates is the level of performance you get out of the system.
I think it's clear you answered the question. It's in the riser, so it kind of floats. But that basically gives the scope of what they were after. Thanks a bunch. Are there any more questions or anybody else has anything else you'd like to ask? Very interesting talk. A lot of potential for the future. I have a question. In terms of cost, I always hear that the hydro stations are these multi-million-dollar enterprises. Yeah, they're very, very expensive. So just give us a scale. What is the cost of your idea or development in terms of, how much? Is it $1 million? Is it several hundred K?
I would say several hundred K. It really depends on how it's implemented. If we're just buying a rack mount system off the shelf, I haven't purchased one recently, but I'm guessing it's on the order of several hundred K. And if the fiber already exists in the form of the trunk cable, it's the cost of the rack mount system plus the labor to install it.
Understood. This is very clear. I think both these things gave us a good idea. And secondly, in terms of installation, how long would a retrofit take? Because obviously we don't want to interfere with existing IMS station operation.
No, that's absolutely true. My understanding is that to put it into an existing system, if you have rack slots and power available to it, and you've got the fibers there, it should be a matter of a few hours, I believe, to install this thing, plus maybe a few days to test it and make sure it's all right. The big trick here, of course, is to make sure that you're connecting to disused fibers and that you're not disturbing anything else in there. But that should be relatively straightforward.
Thank you. I think a very interesting talk. With that, we'll wrap up. Some very nice questions came out of it and a great development. We look forward to, Jeffrey, more of your inputs and collaboration in the future. Thanks a bunch. And with that, let's move on to the next speaker. Thanks, Jeffrey. The next speaker is Carrick Talmadge, and he'll be talking about an external calibration system for Hyperion Sensors. Go ahead.
Yep. Yeah, so I'm here, so you can go ahead and start playing the slide. Today I'm going to be talking about an external with the NTPA intended for use with the Hyperion infrasound sensors. This external calibrator is designed to be remotely controlled so that the Hyperion sensors can be remotely calibrated. The goal of this system is to develop a calibrator that does not require special knowledge on the part of the operator in order to be able to use it, other than knowing how to generate a standard calibrated voltage signal. But the knowledge of the amplitude of the calibrated signal, the sensitivity of the calibrator, and the measured amplitude of the sensor response, the operator will be able to infer the pressure sensitivity of the sensor at a given frequency. The calibrator operates by injecting a pressure signal in the back volume of the sensor. This has the advantage in that it is insensitive to the details about how this sensor was installed. In this image, we show the original piezo driver that was used to inject the signal in the back volume on the sensor, which is on right. It also requires an amplifier, of course, to amplify and drive the driver. The process is illustrated in this diagram where you see a digital input command generated by the operator. The digitizer generates an amplitude with specified amplitude and frequency, which is then produces a pressure signal in the sensor, which then generates a voltage that is read by a digitizer, and which is then interpreted by the operator. This system was then tested at the fax site in Albuquerque, New Mexico. You can see on the top panel on the right, there's a spectrogram showing the generated signal at 1 hertz, which is about 3 pascals, for 3 different pressure values. And in all 3 cases, a measurable signal was observed. So, as said before, one of the goals of this system was to develop a calibrator that could be used without requiring extensive knowledge on the part of the operator about the internal workings of the system. One of the things we discovered was there was a non-uniform frequency response, so that the sensitivity varied with frequency, as shown here. This is probably a consequence of the transition from adiabatic at high frequencies to isothermal at low frequencies. We tested this over 19 Hyperion sensors, and we found a very similar response, which suggests that it's more or less independent of the sensor. It only depends on the properties of the calibrator itself. Similarly, the sensitivity was found to be a function of the input voltage to the external calibrator. We're showing this for 4 different configurations, so they did have different maximum pressure values, and as much as 20% variability was observed. The signal generated in the back volume of the calibrator turns out to be proportional to the static pressure in the back volume. So for a sealed back volume, when the temperature changes, the static pressure changes, and you expect the temperature variability, which we observed from this field station test that we did at Albuquerque. You can correct for it by, if you know what the temperature is, as shown here. But again, this violates the principle that we want the operator to not need to know all these details about how the system operates in order to be able to interpret the result. Here we see the current version of the external calibrator, where we now have Piezo Driver coupled mechanically to the Hyperion sensor, so it works as one unit. And we have a digital controller, which I'll talk about in a minute, which is intended to address the issues that we saw in the previous 3 slides. This slide illustrates the theory of operation of the pressure driver for the external calibrator. There are a total of 8 piezoceramic elements, which are driven by a differential signal from the amplifier. This generates a pressure signal, which is piped through to the back volume of the Hyperion sensor shown on right. This diagram illustrates the internal workings of the digital controller shown earlier. The analog signal produced by the digitizer calibration signal is input to the equalizer on the bottom left. The equalizer is intended to generate a uniform response independent of frequency in the output. The output of the equalizer is fed into a variable gain amplifier, VGA here. The variable gain amplifier is intended to produce a sensitivity which is independent of input level, and then that is fed into the differential amplifier that we discussed before, which then drives the external calibrator. The output of the equalizer is also fed to a level sense, which goes to the microcontroller, and that basically is what's responsible for changing the gain of the variable gain amplifier in order to make a uniform response. The main point of this slide is the microcontroller has an algorithm that is used to take the various inputs, pressure, temperature, and the input voltage, and create an output response which generates a sensitivity which is independent of those three variables. One of the challenges of this project was we needed a higher resolution variable gain amplifier than is commercially available, and so what we did is we generated a circuit using two 7-bit variable gain amplifiers and put them in a summing circuit in order to produce an effective 14-bit variable gain amplifier. This slide shows the effect of the equalizer. The dashed lines are the responses when the control for the equalizer is turned off, and the solid lines are when the equalizer is turned on, showing that we're able to get very good flat stable frequency response. Similarly, here we're showing the correcting for level effect using the level sense as well as the variable gain amplifier. The red lines show the uncorrected version, and the cyan lines are what we get when the level correction is enabled. This slide just demonstrates the effect of the solenoidal valve. When the solenoidal valve is open, the back volume is connected to the fore volume, and you expect a much reduced signal, which is what we get when the valve is opened. This slide illustrates what happens when you change the static pressure from about 99 kilopascals down to about 66 kilopascals. And all we're doing here is demonstrating that our software is able to change the gain in a way which should model the changes in sensitivity of the sensor. The bottom curve actually has two curves, a purple line, dashed purple line, as well as a blue line. The purple is the nominal value that it needs to be, and the blue is what we're actually able to achieve when we measure the effective gain of the system. This is the same illustration, but for temperature. So when the temperature is changed, we're verifying we're able to change the driver sensitivity in a systematic manner to correct for it. As the saying goes, the proof is in the pudding. We have four thin lines, which are when measurements are taken with the level control disabled, and the solid blue lines are with the level control enabled for the same external calibrator sensor combination. We did this at 4 different pressures, 75 kilopascals, 85, 95, 100 kilopascals. And you see there's a significant variability, just as you would anticipate from our earlier results. When the level control is enabled, you effectively get the same result for each. This figure illustrates temperature correction testing done by Sandia. The bottom curve is with the temperature correction enabled, and the top curves showing without it being enabled, and you can see there's a significant improvement in the flatness of response. Finally, this is what we're working on at the moment. We're going to add a digital on-off switch in order to reduce power consumption when the external calibrator is not in use. We're going to configure the solenoidal controller so that the solenoidal valve is normally closed when the external calibrator is powered off. Currently, it's configured to be normally open, which is more useful when you're testing in a calibration tank. For field deployments, it needs to be normally closed so that when the external calibrator is not in use, it behaves like an ordinary sensor. Finally, we're going to refine the gain control models in order to increase the sensitivity about 20%. We're going to refine the nonlinearity model as well as the tilt equalization calibration values to improve the linearity of the frequency response. And after completion of these upgrades, Sandia will commence long-term field deployment and testing, and this will be used to make determinations about the possible acceptance of this system into future IMS field sites.
Thank you very much. A very interesting talk. I think you ran over time, so we have only time for one question. And we have a question here. Go ahead, please.
Yes, so you're using these algebraic models for your gain control and your other sensitivity models. I'm wondering, have you considered a state-based model? So perhaps not a machine learning kind of thing, but something based on state information instead of algebraic models. Algebraic models might have issues, you know, out of the edges.
No, I haven't actually. That'd be something interesting to look at. So far we have, you know, we're able to test over the full range, and I haven't seen too many issues. But you're right, when you reach the top and bottom edges, you do tend to get some worse behavior. So.
Yeah.
Okay, if there are no other questions, let's move on to in the interest of keeping our time limit, to the next speaker. And the next speaker will be Paul Vincent et al. And they're going to talk about innovative on-site infrasound metrology in 2019 and 2020. So this is OSI, on-site infrasound metrology. Please start.
I apologize if I have not been able to connect, and I hope that this pre-recorded presentation will be understandable to all. I present here an innovative on-site infrasound metrology study conducted in 2019 and 2020. In order to improve confidence in measurements made by the sensor deployed on field, on-site metrology is a necessary step. In this framework, a first study has been carried out to estimate a method for field metrology. A short reminder of the metrology activity of the CEA. As we have just said, metrology gives confidence in measurement by ensuring traceability between the measurement and the International System of Units, SI. For infrasound measurements, the French National Metrology Institute, the LNI, in collaboration with CEA, is developing a primary standard. At the same time, CEA has developed a secondary standard with equipment called Eagle, to which a standard microphone is coupled. The last step is a challenge. It concerns the working standards that must be compatible with the site environment. With this development, the CEA has characterized the sensitivity of MD3 sensors, infrasound sensors, according to temperature and static pressure. Here is the first prototype of an infrasound metrology system in the field. The principle is to compare the response of the sensor under test with a reference sensor. The working standard is a HBK 4193 microphone, traceable to the SI through calibration in the laboratory with the secondary standard. For this purpose on field, sinusoidal pressure signals are generated by an infrasound generator to which the working standard microphone is coupled. This is a CEA development, which for the moment is only a prototype. All the equipment is contained in one transportable medium-sized box, another box for microbarometers. There is a multi-channel digitizer, the portable infrasound generator, producing a pressure signal in the infrasound frequency range, and a weather station to monitor the environment. Measurement inside the sensor under test, and in red the working standard microphone HBK 4193. We therefore compare the response of the sensor under test with that of a working standard calibrated in the laboratory. It has been shown that the sensitivity to pressure, static pressure, and temperature can be considered negligible for the microphone in a changing field environment for this first study. So this work has been carried out in November 2019 and September 2020 as part of the installation and certification of the IMS IS-25 infrasound station in Guadeloupe. We remind you that it should be considered as a preliminary experiment for the moment. As you can see, the first step is to set up a tent near the instrument cabinets where the sensor will be placed. The system is placed as close as possible to the site of the infrasound station. The pictures show here the H7 site of the IMS IS-25 station, where the field metrology system has been deployed. The altitude is between 200 and 260 meters, and access to the site requires easily transportable equipment. Here is a detail of the interior of the tent. You can see environment variables measurement, the infrasound generator, the working standard, and MB3 under test. Short information. Here, the hygrometry was about 90 to 90%, and the static pressure 980 hectopascal, which is clearly not the same as in lab. I'm not talking about temperature, around 30 degrees Celsius. A new version is under development and will be ready in 1 year. It is the same concept as the prototype presented earlier, but more transportable, more energy efficient, and more autonomous in measurements. Indeed, it has specially developed low-power electronic equipment capable of measuring the response of an infrasound sensor versus a standard microphone for a whole day on a small 12-volt battery. And the device will also allow the simulation of different altitudes thanks to a system of pump, solenoid valves, and pressure calibrator. Some measurement results are shown here. This is the sensitivity versus frequency for 11 different MB3s at multiple locations in the same infrasound station. The response in amplitude and in phase are compliant with IMS requirements, and we can say that for each measurement it lasts around 45 minutes for one sensor. Here, the aim is to measure the response of the same MB3 in different conditions at different locations. For the results presented here, temperature varies. For the results presented here, the temperature varies from 23 to 32 degrees, the static pressure from 980 to 1010 hectopascal, and the humidity from 40 to 90%. To make the results comparable, the responses were corrected for the model of MB3 sensitivity to temperature and humidity. The dot curve is a laboratory measurement, and the other are field measurements in amplitude and in phase. We can see that the results are good, are in good agreement with lab measurement. This makes it possible to monitor the behavior of infrasound sensors in the field over several years. Finally, I present here the response of the same MB3 at different locations in the laboratory and in the field at different times between 2018 yes, and 2020. As I said before, the possibility of monitoring infrasound sensor in the field over several years is demonstrated here. We have four measurements. So in conclusion, this presentation described the first step in irreversible on-site metrology. It can be seen that laboratory metrology enables the development of on-site metrology. Also, it would appear that the microphone HBK4193 is a good candidate for on-site metrology by comparison. And the study is still in progress with very convincing results, and the new device will be ready in about a year. The method should be validated by scientific publishing in the framework of the Infra-AUV European project Empire metrology project, and there is still the uncertainty analysis to be done. Thank you for your attention. I invite you to visit Guadeloupe after COVID-19, and it's a very beautiful French region. If you have any questions, I can be reached by email. Thank you.
So thank you very much. That was a very good presentation. I think our speaker may not be here live based on what I measured. This was a recorded presentation. I'll just give him a chance in case he has managed to connect. Mr. Paul Vincent, are you able to speak and connect or hear this? Please say something. No. So he communicated with us. That was a pre-recorded talk. With that, I think it was a very nice presentation, and I'll just make a few comments about the presentation. We are familiar with the work because IS-25 was recently completely renovated and brought back. The station was moved, and the station was certified after being moved. And they did do this method that he talked about, the on-site calibration, and the station is performing very well. So at least from what I can say, that the IMS is very happy with the work and support that CEA provided, and that they are working very well and very actively to make these advances something that can be used in the field. Of course, as we all know, there are obviously many questions. For example, what's the cost of a typical system like this? Unfortunately, it's not yet to answer. The second is question that comes to my mind is, for example, maybe he can answer this later on if he hears this from the recording. For example, does this replace having a permanent on-site reference sensor? If you can have a portable sensor that can be taken in the field, or because there are two options. One is to have a permanent calibration facility on site with a reference sensor, and the second, as he pointed out here, a mobile option where you can take something and place there and check and compare and measure what you see with the sensor that's installed. Clearly, there are cost advantages to having the mobile one. You don't have to have a permanent dedicated sensor. So it would be very interesting to find out the pros and cons and advantages of these two. With that, I end the session. I think we may still have some time if there's any late questions that have come in to answer to address to any or all of our speakers today, those who are still present, if there are any other questions that have come in. So if people feel like they'd like to ask something, please send it to the Q&A site, and we can post them to the speakers. If any of the speakers themselves would like to, y'all are live and y'all can talk. If y'all would like to ask each other some questions, y'all can go ahead. We give you a chance to do that. We have a few minutes left. Okay, so I don't hear anything, nor have we received anything yet. Thank you very much for all the speakers for the time and effort you have taken, and also for keeping our session on time. You all did a great job. I'd also like to give everybody a reminder that this is an online meeting, and Science and Technology Symposium is a means for both the audience, presenters, and the PTS staff to exchange ideas, get in touch with each other, get to know each other better. So I'd like to remind you that the presentations are just an opening. It's a method to just begin to know what people are doing and to begin a conversation on both sides. So feel free all through the rest of the symposium to send questions to the Q&A session using the Q&A chat window. And these questions will be forwarded to each of the speakers, and they'll have a chance to directly answer you, because that's the method of getting people to communicate with each other better and know each other and actually directly ask questions. I mean, the formal thing we're doing now is really formal, and if you have a question here, it's great, but really the idea is to get you all to talk to each other, including the staff and members of the PTS. Also feel free to get in touch with the speakers and ask for the question. So without any more questions here, I'd like to thank everyone and for a very good session, and we'll close the session at this point. Thank you.